Welcome to this, the 7th and final session of the Extra Class License course. Our first session will be on antennas and feed lines. Let's begin by looking at antenna patterns. When we're talking about antenna patterns, we're talking about an isotropic radiator, which is a theoretical point-sized antenna that is assumed to radiate equally in all directions. Here you see a three-dimensional radiation pattern of a dipole antenna. The plot on the right shows a slice through the pattern on the left. The solid line in B represents the relative amount of power radiated in the angle shown on the outer ring. We need to learn a couple of new terms. dBd is antenna gain compared to a reference dipole. dBi is antenna gain compared to an isotropic radiator. Gain in dBd equals gain in dBi minus 2.15 dB. If an antenna has 6 dB more gain than an isotropic radiator, how much over a dipole? Well, gain in dBd equals 6 dBi minus 2.15 dB, which equals 3.85 dBd. If an antenna has 3 dBd, what is the gain over an isotropic radiator? Once again, gain in dBi equals 3 dBd plus 2.15 dB, which equals 5.15 dBi. An antenna's gain is the ratio expressed in decibels between the signal radiated from an antenna in the direction of its main lobe and the signal radiated from a reference antenna, usually a dipole, pointed in the same direction and with the same power. A typical beam might have 6 dB of gain compared to that of a dipole. In comparing antennas, it is useful to know their beam width. Beam width is the angular distance between the points on either side of the major lobe at which the gain is 3 dB below the maximum. Here you see that the beam width of a 3-element Yagi is about 60 degrees wide. Which of the following describes an isotropic antenna? A grounded antenna used to measure earth conductivity. B, a horizontally polarized antenna used to compare Yagi antennas. C, a theoretical antenna used as a reference for antenna gain. Or D, a spacecraft antenna used to direct signals toward the Earth. The answer is C, a theoretical antenna used as a reference for antenna gain. How much gain does an antenna have compared to a half-wavelength dipole when it has 6 dB gain over an isotropic antenna? A, 3.85 dB, B, 6 dB, C, 8.15 dB, or D, 2.79 dB. The answer is A, 3.85 dB. What is the far field of an antenna? A, the region of the ionosphere where radiated power is not reflected. B, the region where radiated power dissipates over a specific time period. C, the region where radiated field strengths are obstructed by objects of reflection. Or D, the region where the shape of the antenna pattern is independent of distance. Answer D, the region where the shape of the antenna pattern is independent of distance. There are other useful measurements to be taken from antennas' radiation patterns. Gain is important, but it is not everything. Notice that the back lobe gain of this antenna is minus 18 dB. That means that signals received off the back of this beam will be smaller than off the front of the beam. Side lobe gain and back lobe gain are important for tuning out unwanted signals. With antennas, we have ohmic resistance and radiation resistance. Ohmic resistance, R sub R, causes heat loss in the wire, coax, and materials nearby that absorb the waves, such as foliage and buildings. Radiation resistance, R, is an assumed resistance that, if actually present, would dissipate the power actually radiated by the antenna. Total resistance is the sum of both. Antenna efficiency equals R sub R divided by R sub T times 100%. A halfway dipole has a radiation resistance of 70 ohms and a total resistance of 75 ohms. What is the efficiency? Well, the efficiency equals 70 divided by 75 times 100%, which equals 93.3%. E-plane and H-plane radiation patterns are typically used to picture the overall radiation pattern. The E-plane is parallel to the Earth's surface. The H-plane is perpendicular to the Earth's surface. The vertical angle at which the antenna's major lobe has its maximum radiation is called the takeoff angle. For good dx, we typically want the takeoff angle to be as low as possible. The standing wave ratio is another important antenna characteristic. We like to have the SWR as low as possible for as much of the band as possible so that we can use the same antenna for the whole band. Vertical ground plane antennas are like 1/2 wavelength dipoles. The ground plane makes up the electrical image of the other half of the antenna. We get the best SWR from a vertical ground plane antenna when the radials slope down at a 45-degree angle. How can the approximate bandwidth in a given plane of a directional antenna be determined? A. Note the 2 points where the signal strength of the antenna is 3 dB less than maximum and compute the angular difference. B. Measure the ratio of the signal strength of the radiated power lobes from the front and rear of the antennas. C. Draw 2 imaginary lines through the ends of the elements and measure the angle between the lines. D. Measure the ratio of the signal strength of the radiated power lobes from the front and side of the antenna. The answer is A. Note the 2 points where the signal strength of the antenna is 3 dB less than the maximum and compute the angular distance. Which of the following choices is a way to improve the efficiency of a ground-mounted quarter-wave vertical antenna? A. Install a good radial system. B. Isolate the coax shield from ground. C. Shorten the radiating element. D. Reduce the diameter of the radiating element. The answer is A. Install a good radial system. What is meant by antenna bandwidth? Is it A. Antenna length divided by the number of elements? Or B. The frequency range over which an antenna satisfies a performance requirement? Or C. The angle between the half-power radiation points? Or D. The angle formed between 2 imaginary lines drawn through the element ends? The answer is B. The frequency range over which an antenna satisfies a performance requirement.